Yeah, okay, so today I'm going to be talking about class groups, which is going to take us a little while to get there because there's quite a lot of algebraic preliminaries that we will have a look at first before we actually see the definition, which is quite complicated. So hopefully we can get somewhere today, but we'll see how fast we can go, and then if not, I guess we do another talk another day. So first up, a tiny bit of motivation, because I'm not going to talk about groups in unknown order, because I'm already giving like another talk on that for the Student Research Conference or something. So, but basically that was my motivation for getting into these, is that you can actually generate a random class group and no one really has any idea of how to efficiently compute its order. So it's a nice example of a group of unknown order. So it's a finite group, but yeah, no one knows how to actually compute its order. But you can still do the group operation and stuff. Yeah, so I'll just start off with some definitions, which will ramp up quickly. So firstly is an algebraic number. So we've got a ring R, and S is a subring of R. Okay. And then we're going to call a number alpha in R algebraic over S. This subring. If we can write a polynomial whose coefficients are in S, which has alpha as a root. Okay, so effectively, a polynomial f x in S of x, such that f of alpha equals 0, and then we call alpha algebraic. Okay, and the degree of this polynomial, the degree of the minimal polynomial that we can write the alpha as a root of, we're going to call that degree, we'll also call that the degree of alpha. Okay, so yeah, that's what it means for alpha to have a degree. And if a number is not algebraic, then it's transcendental. Okay, so that's nice and easy. Everyone following so far? Yeah. Okay. So yeah, just to make things more explicitly, a n x n to the plus a 0 equals x. Okay. So all these a n's are going to be in S. This is for an algebraic number, but now we'll define an algebraic integer. Is just basically when the first coefficient is 1, when it's mono. Not mono, when it's, it is mono. Yeah. Yeah, so if a n equals 1, so we've got a polynomial of the form this. Such that alpha is a root, then alpha is an algebraic integer, not just an algebraic number. Okay? So for example, the complex number I is going to be an algebraic integer, because obviously it satisfies the polynomial x squared plus 1. Right? So, and yeah, so it's an integer because it's an algebraic integer because this is mono. Okay. Cool. Everyone good so far? Yeah. Now we will come to number fields. Okay, so a number field is a finite degree extension of Q. So we've got Q, the rational number, and then a finite degree extension of Q, something like this. Is going to be a number field. Okay, we're going to call this the number field. And it just so happens that with Q, any finite extension like this can be written also in terms of just one element. So we can always just write this for brevity. This is always true. So yeah, for example, again, Q of I, if we adjoin the complex number I to this, then we get the Gaussian rationals. And this is going to be a degree 1 extension. When I say the degree of an extension, I mean the dimension is a vector space over Q. Okay, so. But for example, the reals and the complex numbers themselves are infinite degree extensions of Q, so they're not number fields. We're only talking about finite extensions here. Okay. Now, what happens if we consider a specific type of number field where we adjoin the square root of a square-free number? Okay, so D is going to be a square-free integer. Does everyone know what square-free means? It means there's no square dividing. There's no there's no prime dividing D which has an exponent greater than 1. There's no squares that divide D, basically, except for 1. So essentially, because it's square-free, there's definitely not going to be a solution to this over the integers, so this, or over the rational numbers. So this really is a non-trivial extension. But because square root of D that we're adjoining, of course, always satisfies the equation x squared minus D, right? Then this degree is obviously 2, so this is going to be what we call a quadratic number field, okay? Because we're adjoining an element of degree 2 to it, to Q. Now, additionally, if D is negative, then we're going to call this an imaginary quadratic number field, okay? So this is the definition of an imaginary quadratic number field. And if we let D run over all of the square-free integers that aren't equal to 0 or 1, then this will be every quadratic number field, okay? So these are the only possibilities for a quadratic number field. So in this example, I'm only going to care about the case where D is less than 0, only the imaginary case. Imaginary quadratic number field. Q of root D. Okay? Everyone happy with that? And then we'll call the discriminant of this field, which I'll call delta K. This is going to be equal to D if D is equivalent to 1 mod 4. And it's going to be equal to 4D if otherwise. Okay. Now these two cases, you can kind of prove them just by thinking about the generic form of an element in this field, because everything's going to look like this for A and B. And so if you think about the kind of general form of a polynomial that makes this algebraic, then you can kind of derive. No, that's not what I'm talking about here. Ignore that. That's how you would derive the yeah, but there's oh, I forgot what I was going to say about that. Yeah, don't worry. But yeah, you can calculate the discriminant basically in terms of the conjugates of this thing that you've adjoined. So since it's only degree 2, like that, the only other conjugate is going to be root D. And this is kind of like the discriminant of 1, 1, square root d, and minus square root d squared or something. So if you expand it all out and think about the different cases of d, then you can show that this is true. But I'm just going to take it for granted. So that's what we call the discriminant of this number field k. Okay. All right. Now ring of integers of k. Am I going too slowly or too fast? Any questions so far? Sorry if I'm jumping back and forth and you have to keep moving the camera. It's okay. Okay, so we've got k, an imaginary quadratic number field. Now let's consider the integral elements over z. So remember when I defined the like algebraic integers, I said there was a ring R and a subring S. So here we're just going to think about the subring Z, which is obviously inside Q. Okay. So if we think about all of the integral elements over Z, which just means all of the elements which can be written as solutions to equations in ZX, right, polynomials with integer coefficients, and obviously we want the monic ones because we only want to talk about integers, not general algebraic numbers over Z. So these are going to be called we're going to call these the integers in this number field, and they form a ring together called O of k, the ring of integers. These are all of the algebraic integers in k, this number field. And it's not entirely obvious why, if you've got two things which are solutions to monic polynomials, if you multiply them together, for example, that's also a root of a monic polynomial, or if you add them together, it's also the root of a monic polynomial. But it's true, and I'm not going to prove that today, but you can look up a proof online if you want. But yeah, it is a ring, and obviously the number 1 is going to be in here. That's trivial. And yeah, so it's a ring with unity. And I'll give an example. If we consider the trivial extension of Q, which is Q itself, then the ring of integers O of Q is equal to Z. Okay, so this is really why they're called algebraic integers, because it does actually make sense. And another example, if we take the ring of integers of Q adjoined with I, which was the Gaussian rationals, we get the Gaussian integers, Z adjoined with I. So it does make sense in the examples.
Square bracket.
Now because Q, or whatever, is a field, because this Q adjoined with root D is a field obviously has no zero divisors, so any subring of a field also has no zero divisors, and so this is actually an integral domain, the ring of integers as well. And it turns out it's also a Dedekind domain, so that means that every non-zero proper ideal of this ring can be factored into a unique product of prime ideals. It's a reordering. Okay. So that's not true for elements. Just because it's a Dedekind domain doesn't mean that individual elements factorize uniquely, but ideals do. Ideals of this ring factor uniquely into a product of prime ideals. Okay. Oh yeah, what I was gonna talk about was the generators of the ring of integers. You can always write this as generated by 1 and omega. And the form of omega, you can work that out from looking at the minimal polynomial of a like general element in this K. So omega always either looks like 1 plus square root d over 2, or just square root d in those same two cases. Yeah. So that's the ring of integers. Everyone happy so far? Cool. If you've got any questions at all, feel free to ask. Yeah, so everyone knows what an ideal of a ring is? So, yeah, an ideal is just going to be an additive subgroup of the ring, which is closed under multiplication by elements of the ring. So that makes it what's called an R submodule of R. So if we've got an ideal I inside a ring, then I is a R submodule of R, viewed as an R module. Okay, so that's really like, it sounds like there's so many R's involved, but basically it's just saying, yeah, it's contained in R, and you've got this structure where you can multiply by elements of R and still end up in I. Okay, but we can generalize this idea to what's called a fractional ideal. So recall here, I is contained in R, but instead, if we think of, I need to pick a different letter, not K, because I already used K. G. For a field.
L.
L. Okay. L is going to be the field of fractions of R. Okay. So these are all of the elements A over B, where A and B are in R, and B is not equal to 0. Okay? Everyone understand this? So instead of thinking of an R submodule of R, we're now going to think of an R submodule of L. Okay? So this is going to be a subset of the fractions of this ring, but we're still going to have this closure under multiplication by elements of R. Okay? So it's no longer contained in R. It's not an ideal. It's a fractional ideal. Because all of the elements are going to be fractions. Okay? But the key is that we can always pick an element R such that, I haven't actually given this a name, J is going to be a fractional ideal. Okay? So they'll always exist in R and R such that R times J is contained in R. Okay? So you can think of this as clearing the denominators. If we've got a whole bunch of fractions, you can always find a number which you multiply through and it clears out all the denominators, and then you really do have just elements of this original ring. So this is an ideal. Okay? So for any fractional ideal, it's not like true in general rings, but in all of the setting here, then this is true. Then you can always write J as 1 over R times an actual ideal of R. Okay? So you can really think of this. So for example, if we have Z, the ring of integers, then 5Z is an ideal, right? But if we write, like for example, 1 over 4 times 5Z, this is a fractional ideal. Right? Because obviously this little r is just 4. And if I multiply any element in here by 4, it'll jump back into 5z, which is an ideal. Okay, so this is a fractional ideal. Any questions so far? Now we will also define This is like definition after definition after definition, but it will come together. So just bear with me. As long as everyone understands everything so far, that's good. So we can multiply ideals. If we've got two, these are normal ideals now. We've got I and j, normal ideals. We can define their product as all things of this form, where A is coming from I and B is coming from J. Okay? So basically, for any elements in I and J, this is kind of like the ideal generated by them. That's what it means to be the product. So we can do the exact same thing for fractional ideals. Now, if you've got two fractional ideals, I'm just going to like pretend these are fractional ideals now because it's exactly the same thing. If there exists for some I another fractional ideal, I need another letter. M. It's terrible. If there exists an M for this I, such that this product gives you every possible element in the ring, then we're going to call M the inverse of I. Okay? Yeah, but I didn't want to be suggestive. So now I can rename it. And then I don't even need to write that. Okay? So this doesn't always exist for a general fractional ideal. It doesn't necessarily have an inverse. Okay? But clearly R itself, what's the inverse of R? Is R itself. Because obviously the ring itself is closed under multiplication and addition. So this is kind of the identity element. And because we've got inverses and identity elements, all of the fractional ideals that do have inverses, the invertible fractional ideals, they actually form a group under multiplication, and R is the identity for that group.
R is the unit idea.
Yeah.
It's even more interesting.
Yeah. Yeah, because remember also, if an ideal has the element 1 in it, then it is the whole ring, because it has to be closed under multiplication by R. So if you've got 1 in there, you can multiply by every element of R. So this is the exact same thing as the ideal 1. So that might make it more obvious that this really is the identity, because it has the number 1 in it. Okay? So yeah, we've got a group here. The group of invertible fractional ideals. But this is not the class group. We are still not at the class group. Okay. Now I can also write like the general how to get I inverse for a given I. This is usually written in this notation. And you can kind of think of it as like R divided by I. And you get all of the elements in K, which is the field of fractions, because remember this is fractional ideals, such that X times the ideal is contained in R. So yeah, that's the definition. So that's how you actually calculate the inverse. Oh, right. Any questions so far? Everyone following? We're very close. Okay. So we've got this group of invertible fractional ideals. And everyone, yeah, okay, so a principal ideal is obviously an ideal generated by a single element, right? So we had 1 over there, that's the principal ideal, it's equal to R. In that case of 5z, it's kind of generated by the element 5. right? So these are principal ideals, just generated by one element. We can do the same thing with fractional ideals. So we can have principal fractional ideals. They're just fractional ideals generated by a single element. And it turns out that the set of principal fractional ideals is a subgroup of this group of invertible fractional ideals. All principal fractional ideals are invertible, okay? And they're closed as well. So, yeah, obviously, a principal fractional ideal will look something like this, but it won't be an integer. It'll be maybe like 5 over 4, and that would give you this 5 over 4z that we have. Okay. All right. I think that's all we need to actually talk about the class group. So remember, we've got k is equal to q adjoined with d, and d is less than 0 in square 3. So k is an imaginary quadratic number field. Now, the ring of integers, okay. Remember, this was a Dedekind domain, okay? And I said earlier that a Dedekind domain means that we can uniquely vectorize ideals, okay, into products with prime ideals. But an equivalent definition of a Dedekind domain is actually that every non-zero fractional ideal is invertible, okay? I'm not going to prove that those two things are equivalent, but yeah, this is very important. Every non-zero fractional ideal of OK is invertible. Okay. So this group is all of the ideals. All of them are invertible. Yep. And so we're going to call the group of all the ideals J of this number field. Okay. This is the set of all fractional ideals of OK. Alright? So this is a group. Like I said, we can multiply ideals, and the identity is the ring itself, which is OK. And remember, I said that the principal ideals form a subgroup of this group. Okay? So I'm going to call PK the set of all principal fractional ideals of O. And obviously PK is contained in JK. Alright? So that means we can create the quotient group of these two things. So we can take JK over PK. And this is actually abelian. And this is what we call the ideal class group. Finally made it to the actual definition of the title of the talk. Okay, so it's all of the fractional ideals of the ring of integers of a quadratic imaginary number field modulo the principal fractional ideals of that ring of integers. Okay, so this is ideal classes. That's why it's called the ideal class group, because we've got equivalence classes of ideals where two ideals I and J are going to be equivalent if we can write a principal ideal, something like this, times I is equal to J. Alright? Because we're modding out the principal ideals. So this is where the equivalence relation comes from. And we don't even have to worry about fractional principal ideals. We can just write normal ideals like that. Okay? So two things are going to be equivalent as ideals in this class, if in this group, if they are just multiples of principal ideals from each other. Okay. So for any ideal, we can just write the class of all the equivalent ideals with the square brackets, like we normally do with equivalence classes. Okay. And it turns out that there always exists an integral ideal. By integral, I just mean like a normal ideal, not a fractional ideal. An actual thing that's all contained in the ring, I prime, equivalent to I. There always exists an integral ideal in every class. So we can represent the class always with an actual ideal. We don't even need fractional ideals here. And again, just like before, it's pretty easy to see that the principal ideals, all of them are obviously equivalent to the principal ideal of 1, which is the whole ring. This is the identity. Okay? Because if we multiply any ideal by a principal ideal, we still get an equivalent ideal by definition. So this is the identity in this group. It's just the denominator of this equation, right? Yeah. So that is the ideal class group. And I guess we can think a little bit about like what it means, what this group actually means. So if this group is trivial, what does that mean? That means that every fractional ideal is principal, right? If this is trivial. So the size of this ideal class group kind of measures how far away from that case we are. If this is trivial, then we're in the case where every fractional ideal is principal, so we've got a principal ideal domain. Okay? But if it's greater than 1, if the size of this is greater than 1, which we call the class number, then we're not a principal ideal domain. There's some ideals we can't write as principal. So the bigger the group gets, it kind of represents how far away from that case we are. So for imaginary quadratic number fields like K, the only cases where it's trivial is -1, -2, -3, -7, -11, -19, 43, 67, and 163. Those are the only cases where this group is trivial if D is less than 0. Which is kind of weird, right? Like, why are these specific numbers? Why is there only this many and that's it? And it took quite a long time for people to prove this, but it is proven. Whereas if you go the other way and you say, looking at the... What was that?
Can you just repeat it, please?
These are the only cases, these D values, are the only cases of imaginary quadratic number fields. So the only values of D less than 0 that have an ideal class group that's trivial. Okay? So I'll call the class number, it is normally written with an H, right? Yeah, this is the class number. It's the size of JK over PK. The size of the class group. So in this case, it's always equal to 1. Okay? And the only cases that it's trivial. Every other choice of D is non-trivial. Whereas if you think about the cases where D is greater than 0, no one knows how many are trivial. No one knows if there's infinite or finite or anything. Nothing's been kind of shown. So it's kind of interesting as well that people have done this for negative but not for positive. So yeah. Now I guess why it's interesting to me, like I said at the start, is that if we just pick a really big D here and take this class group, then how do you compute this? No one knows. There's like very inefficient methods for computing this class number. So if we make D really big, then this becomes like theoretically infeasible to compute. And so that, yeah, like I said, that gives a method for generating these groups of unknown order, where you can just generate a group and you can play around with its like elements, and you know what the identity is, and you can write down the operation, but you have no idea how big the group you're working with. It's always finite. I'll just make a note. This is always finite, but yeah, like I said, no one knows how big it is. Okay? All right. How am I going for time? I've still got a little bit. Any questions so far?
Is it obvious that it's 5?
Probably not, but it is. I don't know how to prove it. It's finite.
You say an easy case that you know how to compute that.
An easy case.
Yes.
Well, only if really if you can like. There is an algorithm to do it. It's just really inefficient. So I guess if D is small enough, then the algorithm's easy. But yeah. I don't have any examples put on the board. I'm not going to run through it. I don't know how the algorithm works. But yeah. So another really interesting thing, well I think it's really interesting, about these groups, these ideal class groups, is that there's actually this interesting relationship with binary quadratic forms. Okay? So maybe I'll just leave this here. And maybe I'll just add that definition of the discriminant again. So remember, this was equal to either D or 4D, depending on whether D is. So this is the discriminant, okay? So there's this really interesting relationship between this group of ideals, modulo principal ideals, and composition is multiplication of ideals, and binary quadratic forms, which are binary because they're written in 2 variables, and quadratic because they're degree 2. Okay? And we're going to only care about integral binary forms, where A, B, C are integers. Okay? And we can define the discriminant of this as well, of the form, so of course F. The discriminant of F is going to be equal to B squared minus 4AC. Okay? Now, the really interesting thing is that this discriminant and this discriminant are linked somehow. Okay? And I do not have any way to explain why this link exists, but basically if we fix this, then all the forms with this discriminant form a class group that's isomorphic to that. Okay? So what do I mean by classes of quadratic forms? So if I think of fxy, and maybe like f of 1 and 1 equals 3 or something, this means that f represents 3. Okay, we're going to call it represents. So all of the integers that f represents are just the integers which there exists some x and y that could be there as an answer. Okay? 2 forms, f and g, are going to be equivalent if they represent the same integers. Okay? Does that make sense? So we can write this a little bit more concretely if we say that f and f prime, or f and g, are equivalent if there's an invertible linear shift of these variables x and y, okay, which we can write as a matrix alpha, beta, gamma, delta. No, not that delta. Such that the determinant of this, well, I guess just such that it's in the special linear group. And this times like x and y as an input to the other one gives you the other form. Does that make sense? Sorry, that was really badly worded. Kind of like this. If f of alpha x plus beta y, gamma x plus delta y equals to g of x, y. Like that. So some linear combination of the two gives you the other one. Okay, that's what it means for as well as invertible. This is still important. Yeah. So we can again just think of ideal of classes of polynomials under this equivalence relation. Okay. And just like over there, how I said you can always pick an integral ideal to represent the class. Here we can always pick what's called a reduced ideal, a reduced form, which is kind of just the smallest. That's just a definition of like how small a form can be. So a form is reduced essentially if. Important thing that I forgot to mention is that we only care about positive definite forms. So that just means that all of the integers they represent are positive, strictly greater than 0. This means essentially that a is greater than 0 in a reduced form. Okay. So yeah, a reduced form is basically just saying that b has to be bounded by a and minus a. So b is somehow smaller than a, and c is also small. No, c is bigger than a. So you've got some like ordering on the size of these, and you kind of say it's the smallest one of these, so that the coefficients are all as small as they can be. But anyway, it's not really important. I've got the notes here as well. Just going to put them online if you want. And again, we've got an identity, which we can explicitly write down, is the form whose coefficients are 1, 1, and k, if delta is in the form 4k plus 1. And in the other case, it's going to be 1, 0, and minus k if delta equals 4k. So these are the same two cases we had here. Essentially, if delta is 1 mod 4 or not, or 0 mod 4, then we care about this k, which is the same as that d up here. So that's the identity element. Does everyone understand what I mean by these three numbers? It just means like a equals 1, b equals 0, and c equals minus k. Right. Yeah, okay. And the inverse of a form ABC is just a minus b and c. But this isn't reduced. So if ABC is reduced, then if you make b negative, it's no longer reduced, but you can always reduce it using the reduction algorithm and find the canonical representative of that class. But it's really easy to invert. So, yeah. And so that forms a group. And the group operation is this complicated thing called form composition, which came from Gauss, I think. And it's exactly the same as multiplication of ideals under this isomorphism. These two groups are isomorphic, and it's, yeah, like I said, it's really weird. I don't know why they are, but it is. So if we pick a delta fixed, then the class group of fractional ideals of delta is isomorphic to, I don't know what I'm going to call this, the form class group of delta, which just means all the equivalence classes of positive definite binary quadratic forms whose discriminant is delta. So, and this is a lot easier to compute with. This is, if we want to do operations in the class group, it's actually way more efficient to do them here and just map back and forth. And there's an explicit.
Is it an obvious isomorphism?
Obvious.
Yeah, is it hard to compute everything?
Oh no, it's not hard to compute. It's like you take the ideal norm or something. Yeah. No, it's not hard to compute it, and it's not hard to, for example, reduce a form or even to compose two forms. There's explicit algorithms and they're fairly efficient, but they're not like mathematically obvious. They're just algorithms. So, yeah. Okay. Well, yeah, that's basically what I wanted to talk about. So, any questions? Don't ask me why these are isomorphic. I can't see it. There's maybe like an advanced level of maths where you can see that this is isomorphic easily, but for me they're just two random groups that are somehow the same. So even looking at the isomorphism between them wasn't really enlightening. So maybe it would be for you, but yeah, I didn't write it down.
No, but it's a norm.
Do you want me to find it?
It's a factorization.
Do you want me to find the explicit isomorphism? I think it's here.
Only one thing that's not immediately obvious to me is why class group should actually be found.
Yeah, you can look up the proof. So the ideal of this is the isomorphism of ABC is equal to AZ plus or minus B plus the square root of delta E 2. No, just the square root of that's one direction, so that's easy. The other direction, if you take an ideal line, then it's just the norm of alpha x minus beta y over the norm of the line, where alpha and beta are a basis of the fractional ideals of the Z. And this is obviously just the ideal, the norm. Yeah, so that's not very enlightening to me, why this is, like, it's nice, there's a nice form to write down, but it's not, yeah, it's not clear to me why this is, why this connection exists in the first place. In either case, if you fix delta, then you can always represent this as just two elements, right? A and B, because you can work out C as
I can kind of see where it comes from, if you think about it. Because this representability question, you can also ask it in terms of norm forms. Exists there an element such that the norm represents an integer? If you think about it, what I've written up here is just a norm form where you will let the enters vary. So I can kind of see where it comes from.